Now, welcome, my fellow listeners. You are welcome to Learn Elite Academy. Now, today is another day, and we are here to do a video on physics topic current electricity. But under this current electricity, on this video, we want to be talking about Ohm's law, ohmic and non-ohmic conductors, properties which the resistance of a conductor depends, resistivity and what? Conductivity. These are the things we want to be talking about in this video. Now, first of all, what is electricity? Electricity is the instantaneous flow of electric what? Current. Now, when you walk around the street towards the night, when the day is dark, when you are walking, you cannot walk in darkness, you see light everywhere. When you see the NEPA light, whatever, all those are electricity you are seeing. You understand? So when we say electricity, we say that is the word instantaneous flow of electric what? Current. Now, what is current we are talking about? Electric current is the rate of flow of charges around the world, a circuit or a conductor. I come again. I say electric current is the rate of flow of charges around a circuit or a conductor with what? Time. That is what we call electric what? Current. And dimensionally, we can denote, I use the word dimensionally, we can denote electric current as this. This is symbol. And this is the dimensionally representation of electric current. This is how you dimensionally represent it. That's why I said that dimensionally we denote it as this. You understand? So now when we take this as electric current, what I want you to know is that current, when we say current R is charge over what? Time. Take note. Current, we said that is charge over time. Take note. This is the formula for what? Current. Are you getting now? Now, but I want you to know, if we take it like that by symbol, I can take it as what? Charge over what? T. We can take it like this. But now, according to quantization of charge, I want you to know that in this case, we have the I here. This I stands as the what? The current. The Q there is stand as what? The Q there stands as the quantity of what? Electricity or charge passing through the what? The conductor. While T there is the time, which the time, the duration. Now you get it now, that's the time. Now I want you to know that current, we measure it in ampere. When somebody talk about current, current is measured in ampere. Take note, ampere, the unit of, we use ampere. Ampere, A. This is the SI unit of electric current. While charge, we measure it with coulomb. Coulomb C. The unit of charge is in coulomb. While time, T, are you there, which is second. We talk about the unit of what we call the time is second, S. So A here is ampere for the unit of current. Q here, which is coulomb, C, we use it now. While T is second, S. But now I want us to look at it briefly here when we talk about the law of quantization of what? Electric charge. Now we want to talk about the fundamental law of what? Charges, which also known as the law of quantization of what? Electric charge. What does it state? It states that the magnitude of charge. Are you getting now? The magnitude of a what? A charge is the what? The integer multiple of the electronic what? Charge. Take note, I come again. It said that the magnitude of a charge is the integer multiple of the electronic what? Charge. What do we mean by this? I want you to understand that in this case, take note. Charge, when we say charge, this is Q, is given as this. This is what we are talking about. That the magnitude of the charge is equal to the integer multiple of the electronic charge. That is what we are talking about now. Are you getting now? And this is the charge. This N here stands as the number of electronic charge, or you call it the quantum number of electronic charge. You can say E there stands as the word electronic charge. But this E here is constant. We take it because you know that the E here, when we talk about charge is either built up by proton or what? Electron. You must know that a charge is built up of proton and what? Electron. So when we say charge here, electronic charge, if it's electron, it becomes minus 1.6 times 10 raised to the power minus 19 coulomb. It's a constant, the E is a constant, take note of that. But if it's for proton charge, it becomes plus 1.6 times 10 raised to the power minus 19 coulomb. Take a good note of what? This. Are you getting that? So because of that, I can come here and I will say that this charge here can have a Q over what? T, which is the same as this over T. Or I cannot say therefore charge can have an I what? IT, which is N what? A. Please take a good note of what? This. But another thing I want you to look at here is that we want to look at the device, the instrument using in measuring what? Electric what? Charge. Now when we are measuring charge, electric current, let me use the word electric current, not charge now. The instrument we use in measuring electric current, we use a galvanometer. If we want to detect a charge, a smaller word, current in a system, maybe you want to detect current, small current, we use the galvanometer. But if it's a large amount of current, we use the ammeter. Take a good note of that. The ammeter is used, it's a device used to detect or to measure a large amount of current. Galvanometer is a device used in detecting a small amount of what? Current. So you must know the difference between the galvanometer and what? Ammeter. Take note of what? That. From here, I want to go on down to what? Ohm's law. Now, when we look at Ohm's law, what does Ohm's law state? Ohm's law states that it says the current that passes through a metallic conductor at a constant temperature is directly proportional to the what? To the potential difference between its end. We are looking at Ohm's law. It says that the current that passes through a metallic conductor is at a constant temperature is directly proportional to the potential difference between its end. That is to say, what we are saying here is this. If I say current from Ohm's law, what we are saying now is that we are saying that voltage varies directly as the current. Meaning voltage increases with current. You get it now? It's directly proportional now. But look at something here. In other words, I cannot say that therefore V, because if it's proportional, we said that temperature is what? Constant. This is what we said. Are you getting now? If temperature is constant, we cannot say now this becomes equal to what? I what? R. What does arrow signify? Resistance. Arrow here signify what? Resistance. And what is this resistance for? Listen carefully. The resistance is the opposition offered by the wire to the flow of the current. We call it resistance. Look at it. Arrow is the resistance. Is ohms. Is the constant. This arrow here. So we say that V, we say it's I what? R. Arrow here is the resistance. Every material that conducts electricity has what? It has its own resistance. And what is this resistance for? The resistance is the amount or the opposition offered by the conductor, the material, to the flow of the current is what we call this resistance. And we take it, it's being a constant, we can say that R becomes equal to V over what? Current. We take it like this. So this statement here is constant. This is a constant. So whenever you talk about V over R, we are talking about the ratio of voltage to what? To current is constant. We call it what? Resistance. And resistance, the unit for this resistance is what? Is ohms. Ohms, this is the symbol. Ohms. Let me put it. Ohms. This ohm, look at it. You see now, we use it in representing, it's a honor to the man. Ohm, the man that stated the law, they have to honor it. But this is the symbol. Ohms. Are you getting now? V there is the voltage. The PD, the voltage here now. That is the V. And it's in volt. The unit is in volt. Are you getting now? You all know that current is what? We all know that it's the ampere. Ampere. So when we say resistance, here we said it's ohms. And what is ohms? Take note. When we say 1 ohm is equal to what? 1 volt over what? 1 what? Second. Please take note of that. Sorry, over 1 ampere, not second. 1 ampere. Ampere. 1 ohms is 1 volt over what? 1 ampere. 1 coulomb of what? 1 volt, just one not coulomb, 1 volt over 1 ampere. That is what it means. But when we say the 1 ohms is that, are you getting now? Take note of that. Now, another thing I want you to look at now, we are looking at this now. We are talking about resistance. So, in other words, I can say that current here cannot be voltage over R according to this law. If we say voltage is IAR, voltage is IR, we cannot say that current cannot be voltage over R. Remember the other time we said that current is what? Is charge over time. We remember we said that is this over what? This. So look at it. This is the relationship they are keeping. That current is this, is this, is this. We can take current as what? That in electricity. Now from here, we want to now look at number 2. We have just discussed what? Ohm's law now. Let's look at ohmic and non-ohmic what? Conductor. We want to look at ohmic and non-ohmic what? Conductor. What are ohmic conductors? Ohmic conductors are conductors that obey Ohm's law. Conductors that obey Ohm's law, we call them ohmic what? Conductor. What kind of conductor is that? For example, we can talk about metals. All metals obey Ohm's law and some resistance. All metals obey what? Ohm's law and some what? Resistance. Why are they obeying? Why metals are obeying Ohm's law? Why some resistance are what? Obeying Ohm's law? The reason is this. In ohmic conductors, for example, when we talk about silver, now, we can say that the voltage has a linear relationship with current. That is why they are obeying what? Ohm's law. Any material that obeys Ohm's law, it means that current and voltage has a linear what? Relationship. Just as we stated here just now. When I said that voltage varies directly as what? Current. So the linear relationship they are keeping here is the resistance. That voltage is equal to I what? R. Therefore, resistance is voltage over what? Current. You can see resistance now. So in all ohmic conductor, the ratio this is constant for all ohmic conductor. For silver, gold, copper, all this one is constant for them. Please take a good note of that. They will ask you such what? Question. That the ratio this is constant for what? For ohmic what? Conductors. JAMB will ask you, WAEC will ask you, GCSE they will ask you, NECO they will ask you, Resistivity they will ask you. Any exam you go, they will ask you. So you have to take note of this. That this is constant for all what? Ohmic what? Conductors. Now let's look at now. Like why I ask a question now. They obey Ohm's law because why? All metals obey Ohm's law because voltage and current they have the linear what? Relationship. Now let's now look at non-ohmic what? Conductors. Now when we talk about non-ohmic conductors, we are talking about conductors that does not obey Ohm's law. Conductor that does not obey Ohm's law, we call them non-ohmic what? Conductors. For example, we talk about liquid. Liquids, they conduct electricity, but they does not obey Ohm's law. Because in liquid, voltage and current does not have a what? A linear what? Relationship. For example, when we talk about electrolysis, when we talk about Faraday's law of electrolysis, when that says that, he said the mass of element, look at me, mass of element liberated during the process of electrolysis is directly proportional to the quantity of electricity that passes through them. Now, if you look at it very well, now we said that mass here becomes this. Look at it now. Z is the electrochemical what? Equivalent. So what we do, we know that Q, when we said that Q is IT. Now, for what we are saying now, I told you that mass of element become equal to this. This Z here stands as the electrochemical equivalent. While the Q here is the quantity of charge. Remember we said that charge is IT. So meaning we can write this as ZIT. Now if you look very well, current is here, there's no voltage here. So voltage and current have no linear what? Relationship. But in ohmic conductor, look at it here. You have current and voltage, they have a linear relationship with the what? Resistance. But here now there's no linear what? Relationship. You can talk about voltage and what? Current. Now, let's look at this picture here. I want you to see something here now. Now, when we talk about non-ohmic conductor, what are they? I talk about liquid, for example now. I talk about thermionic devices such as diode. We talk about transistors. All these are non-ohmic what? Conductors. Glass, wood, they are non-ohmic what? Conductors. Are you getting me? So in other words, if I come here like this, I can come here now and we look at it now. Listen carefully. The graphical representation of ohmic conductor and non-ohmic conductor, look at them. When they talk about graph, the relationship between voltage and what? Current. Like the one of voltage, Ohm's law, I told you they are linear. But the one of ohmic conductor, they are not linear. Look at it very well. Now, for ohmic conductors, it will give you a straight line from origin. And the slope of the graph is always, it gives you what? The resistance. Look at me. For example, Ohm's law, this is it. Look at it. This Ohm's law. This is it. For Ohm's law, there is what? Current. Here is what? Voltage. Now, if you look at it, it starts from the origin. Look at it. From the origin, it's a straight line. This is a linear graph. It tells that current and voltage, they have a linear what? Relationship. But if you come here for what? For example, like diode now. If I want to look at diode, I want to look at what? Diode. If I want to look at diode, look at the graph. The graph is something like this. It will come like this. Look at it. It comes like this. It's not a straight line graph. It's a curve. You look at it. Let me show you very well now. Look at it. It's a curve. Look at how it looks like. It's a curve. This is for diode. You see, this is current and this is voltage. This is for diode. Look at the one of ohmic conductor. Look at the one of non-ohmic conductor. Thermionic device is diode. Now look at it here. You see now? Now, current and what? Voltage. But look at transistor. Transistor is not this. When you now come to transistor, it's not something like this. Here's what? Current. And here's what? Voltage. This transistor. So these two, they are for non-ohmic conductor. Why this one is for ohmic what? Conductor. Now, another thing we want to look at here is this. We want to briefly talk about the properties which the resistance of a conductor depends. The properties which the resistance of a conductor depends. 1. Temperature. The resistance of a conductor depends on what? Temperature. It depends on the length of the material. That's number 2 now. Number 3, it depends on the thickness or the diameter. The thickness, the diameter, or the area of the what? The material. And lastly, number 4, you talk about the nature of the material or what? The resistivity of the material. So these are the 4 things. 1, temperature. 2, length. 3, area. Area which is or thickness or diameter of the material. You understand? 3. Number 4 now, we now talk about resistivity or the nature of the word material. So from here, we want to briefly look at the term resistivity. Now, from here, we want to look at what? Resistivity and conductivity. Now, what do we mean by resistivity? What is resistivity? Now, the resistivity of a material, when we talk about resistivity of a material, is the resistivity of a material help to quantify. Are you getting now? We can say, let me put it like this. I will say that the resistivity of a material is an intrinsic property that help to quantify how strongly a given material opposes the flow of what? Electric current. I come again. I said that the resistivity of a material is an intrinsic property that help to quantify how strongly a given material opposes the flow of what? Electric what? Current. Or somebody can say that the resistivity of a material is the resistance of cross-sectional what? Area. Cross-sectional surface area per unit length. You can still talk about that. Let me show you something. If you are given a wire, normally you know that your wire, normally they are thick. Now, when we talk about thick wire, listen to me. If this is going to be a wire, let's look at it. Let's look at it. You know this is a wire. If we take this as the length of the wire, let's look at this the length of the wire. If a wire is given to you like this. Now, remember in the wire, inside you see some other smaller wire. Red, black, another color inside. Remember this is the thickness. So if I take from here to here, as the thickness, I can say this is the diameter. When I was talking about, I say it depends on the diameter. Or I can talk about the surface area, the area here. Area. This is the cross-sectional surface what? Area. And you must know that this wire has its own what? Resistance. You must know that. It has your resistance and what? Resistivity is constant. So now, the resistivity here is the constant. But I want you to know that here, in mathematics, we know that diameter. When we say diameter, since this is a circular body, this circle, diameter is 2 radius. 2 radius, you must know that. That diameter is 2 radius. So meaning that the diameter of the wire becomes this. So in other words, we cannot say that therefore, radius becomes diameter divided by what? 2. Take a good note of that. So now, we now look at the area. What is the area for? The area of this material, the cross-sectional surface area. A. You can look at the surface, it's a circle. We can say that it's what? Pi r square. This is the surface area. So we can still take it as what? Pi r is what? D square over 4. Because if r is d over 4, this d over 4, when you square it, it becomes this. Look at this r square now. Are you getting now? That is why we carry this d over 4 and square it, it becomes d square over 4. This becomes what? The area. Or in another way round, if I want to look at it now, like for example, now this is it now. Now, take note of this. But now let's come back to what? Resistivity. What is now the resistivity? When we are looking at the resistivity here, I want you to know that the resistivity, the resistance of the wire, varies directly as the what? The length of the wire. Take note of that. The resistance of this wire varies directly as the length of the wire. At the same time, the resistance varies inversely as the what? The cross-sectional area. So meaning that the resistance here, the resistance of the wire decrease. When the wire becomes more thicker, as thick as the wire, when the wire becomes thick, the resistance what? The area decrease. So the area decrease with what? The resistance. While the resistance increase with what? Length. Look at it, that is why it's this. So in other words, according to joint variation, I can add these two together now. I will say that resistance here can now be this, length over what? Area. It becomes like this. So in other words, I can say, now, we say that resistance varies directly as length and inversely as area. So in other words, therefore, I can say that resistance can now be equal to the resistivity, which is the constant, length over what? Area. It becomes like this. So this is now the word, the formula. One of the formula we are looking at. So now, this symbol here, this is the resistivity of the wire. This is the length of the wire. And this is the word, the cross-sectional surface area of the wire. This is the resistance of the wire. So in other words, I cannot say that therefore, resistivity now, which is this, I cannot say that is AR over what? Length. This is the formula for what? Resistivity. Take note of this formula. This is the formula for resistivity. But in a question, maybe you were given what? Pi. They gave you diameter. They gave you radius. How do you go about it? You can come like this. You can say that here now, area is pi r square r over what? Length. This is it. When they give you resistance, the radius of the wire, look at it here. But if they give you diameter, it becomes like this. You now work on it now. Diameter now. It becomes pi d square r over 4 L. You have it like this. So please take a good note of this formula. It's very, very what? Useful when it comes to what? Resistivity. But another thing again I want to tell you is this. When we want to look at this resistivity, let's go more detail a bit. Look at it. Now, if a wire is given to you, take for example, when two material, let's say the same material is given to you. Are you getting now? And they are talking about they have what? Now, for the same material, for material of the same resistivity, when it's given to you, are you getting now? In a case like that, we can say that the resistivity, when the resistivity becomes constant in that of the material, we can say that initial resistivity becomes final what? Resistivity. For of two materials that are similar, for similar material, that's what I'm trying to say. When they say similar material, this meaning material of the same resistivity, it means that resistivity is constant. So in that case, initial becomes what? Final. If a body A and a body B have the same word, resistivity, they are similar. In that case, we can say resistivity of A is equal to resistivity of what? B. So in this case, what is the formula I gave to you? Look at it here. In a case like this, I will say that A1, R1 over what? L1. We can take it like this. Take a look at it. Which is equal to what? 2 R2 over L word 2. Look at it. For similar word material, you can take it and use this very well. Another way, sometimes they will say calculate the ratio of the resistance. Listen carefully. The ratio of their resistance in a case like this. When they say the ratio of their resistance, look at me. You use the formula like this. You say that arrow 1 over arrow what? 2. We can take it like this. Take a look at this. For similar material. In this case, we give you A2 over A what? 1. In bracket, look at it. We can come again. Are you getting now? We can say that L1 over L what? 2. We can take it like this. For similar material, listen to me. When I say calculate the ratio of the resistance of the other one to the first one to the second one, this is the formula. Or we can take it as well. Remember that our A here, A is pi arrow square. So if they give you radius, it cannot be arrow 2 over arrow 1 bracket square. Look at it. For concentric circle, you have it, that is the area now. So now area here become arrow square. Because if it's pi, if here is arrow what? 2, pi arrow square 1. This pi can cancel pi. Arrow square 2, arrow square 1. We can write it as arrow 2 over arrow 1. We can take it like this square. That is why I put it there in place of A, which is the same as L1 over L2. We can still take it like this. But if the diameter is given to you the same, we can take it as D2 over D1 bracket square L1 over L2. That is for similar word material when they are talking about resistivity. So this formula is very, very useful. With it, we are going to stop here. Make sure you follow us in part 2 of this topic. We'll be going to another area part 2. But now I want you to know this. Always subscribe. You know we are here for you, like I said. Always subscribe. Don't just watch it and go. Always subscribe. You understand? When you are subscribing, it shows that will give us more energy to go on with you. Are you getting me? So try and do that. In our next class, make sure you follow us. We are going to be dealing on this topic in detail. We are going to use all this formula to solve problems. God bless you.